Morning, everybody. How are you doing? Hopefully well. A couple things to talk about today. So I wanted to go through a couple examples from this organic structures thing from last week. Hopefully you've had a chance to try some of these. If not, please do so. And then we're going to also look at the polarity and intermolecular forces material for the next part. And then we'll look at the ICP data from lab yesterday. All right, so let's take a look at a couple of these first. I forgot I had trouble with this yesterday, but I will attempt to copy some of these over so that we can see them. I'm gonna have to come up with a faster way of doing that at some point. But okay, so there's some. So let's take a look at some of these and how we would figure out the structures. We looked at a couple of them earlier. So let's take a look at, what is that, L? I think that's an L. So we've got CH2 double bond, CH, CH2O, CH2, CH, and then CH3 taken twice. As we talked about last time, the best way to do that is first to break it up into a condensed structure, but with the lines. That way we will be able to see how it's put together before we try to convert it straight to the line structure. So to do that, we basically leave it intact. We just add some lines to show how things are connected. So instead of it running all together, we just split it up a little bit. And then this last part, remember that when we have CH3 taken twice, we can't put those two in a row because that one carbon would have too many bonds. So, and then this carbon with the CH wouldn't have enough because it needs 4 and it right now just has 2. So that means it needs 2 other things connected to it, and those are the 2 CH3s. So there's our also condensed structure just expanded a little bit. Now if we want to make a line structure from that, we can think about how long of a chain we're going to have and what types of elements are in there. So I see 3 carbons, then an oxygen, then 3 more carbons, and then we've got this extra carbon coming off this way. So I'm going to go 1, 2, 3, then an oxygen, then 3 more. And then I'm going to just count them again to make sure I've got it right. So 1, 2, 3, oxygen, 1, 2, 3. Yep, got it. Now I've got a double bond between the first 2, so I want to make sure to get that in there. And then the last thing to do is to add the CH3 coming off of the second to last carbon. Again, I can put it either up or down, but just for the nice geometry of the structure, I'm going to put it up. So that's what that one would look like. All right, and then finally, as a challenge, let's take a look at the very last one. So the very last one is quite big. I don't even know if I'm going to be able to get it all on the screen, but we'll do what we can here. It is a very, very large structure, but the technique, the idea, what we're doing is really the same thing. So hopefully that will help us out here. We've got CH3, CH2, CH2 taken 3 times. So there's going to be 3 of those. All then connected to that next carbon. Again, they can't be connected in a row because then there wouldn't be enough bonds on the carbons. All right, so all 3 of those are going to be connected to this next carbon. That's not really a geometry that we like to draw usually, but once we convert it to a line structure, it should look a little bit nicer. All right, so then from there, we've got that C, then we've got O, CH2, CH2, and then CH. O, CH2, CH2, CH, and that's the start of this double bond here. All right, so then from there, we can go a double bond to another CH, CH2, CH2. I'm just kind of reading from left to right here. CH2, CH2, O, C, and then we've got 3 more groups. So all 3 of those groups are going to be coming off that last one again. And these are slightly shorter groups than the earlier ones. All right, sorry, the drawing's being a little slow here. Okay, so there's our condensed structure kind of all the way out. Doesn't even fit on the screen, it's so big. So we're going to do the same thing that we've done before with line structures. We just got some more stuff to add. So don't be scared off by the giant structure here. We just have a few more things to add. So we've got I think of this as 1, 2, 3, 4 carbons. We could start up here too. It doesn't matter. 4 carbons, then an oxygen, then 2 carbons, then a carbon, or let's just do it as a whole thing. So 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. 1, 2, 3, 4. Okay, then an oxygen. Then 1, 2, 3, 4, 5, 6 more carbons. 1, 2, 3, 4, 5, 6. And then another oxygen. And then a carbon. And then 2 more coming out from the end. Whoops. I accidentally wrote that. So 2 more coming out from the end. So that should take care of it. Now we have some other stuff to add. We've got 2 more groups of 3 carbons coming off of the one that's connected to the O. So that's this carbon here. So we need to fit a couple more in there. It's not going to look great, but something like that is fine. Then we've got a double bond to add in here, and the double bond is the 3rd carbon from this oxygen. So oxygen, 1, 2, 3, and then that's double bonded to the next one over here. Then we should have 2 more CH2s, yep, and then another oxygen, then a carbon, and that's also got these 3 groups coming off of it. Each one is a CH2, CH3 group. So we've got 1 in there. We need to put in 2 more. So something like that. And there's that big giant structure. So hopefully that's what you got. If it's not, compare and see maybe where you went wrong. But at this point, when you finish this, you should be able to do this kind of thing. That's how you can assess yourself on that. All right, so I'd be happy to go through any more of these. If you have questions, if you want to go through the ones that you worked on, just let me know. We can always meet and take a look at that. For now, I want to move to the other material for this week. So let me pull up that polarity thing. All right, so there's a few different resources linked on Blackboard and here, but I think this is the best one, and you might want to use those other ones as a way to fill in some knowledge or make some stuff make sense if this doesn't, because there's a lot here. But hopefully if I go through it with you now, it will make some more sense and you'll be able to work through it. These things also, by the way, work great in groups. So if you know a couple of people from class at this point, from lab, you can work on this together, either in person or online. That can make it work a lot better if you're able to discuss it. All right. So like the other ones that we did before, what's happening here is you have a whole bunch of data without really much explanation. And then it immediately starts asking you questions about it, even though you haven't necessarily, figured out what all that means yet. But the questions are meant to lead you through it and kind of make it make sense. So a few things that we should talk about before getting into this. Polarities. So the idea of polarity is that in a chemical bond, you've got two shared electrons, but those electrons may not be evenly shared. So the electrons might be pulled more toward one atom than the other. And that that's called, or that's determined by something called electronegativity. It's called polarity, and that resulting bond is a polar bond. And the importance of that is that those bonds end up giving you, and actually let me draw this a little bit here. So they end up giving you some ways of molecules can attract each other. So if we take a simple molecule like hydrogen, H2, and we think about where the electrons are in this molecule, we draw it as two letters in a line, but really they're these clouds that are kind of mashed together. And that kind of makes this cloud of electrons that goes all around the whole molecule. And those electrons are shared pretty much evenly, because why would they go to one side versus the other? That they're the same on both sides, so there's not really a drive to pull them to one side or the other. If instead we have a CO bond, we have a little bit different situation. O pulls those electrons more strongly than C. And so you get kind of this lopsided electron cloud where the electrons are more around the oxygen than they are around the carbon. So they spend more time here. We can say more electrons. They're not really more electrons, like it's still two electrons, but they spend their time more on this side than on this side. And that results in something called polarity, which is a separation of charge. So electrons are negatively charged. So if the electrons are more on this side, then this side gets a little bit more negative, and this side gets a little bit more positive because the electrons are not there. So we end up with this little bit of separation. It's not a full separation like an ion, but it's enough that these molecules can now attract each other because of that lopsidedness of the electrons being favored over to one side. So all of that is saying that we can look at these data to figure some stuff out about this concept. So we can see that there are some molecules here with condensed structures that we've seen before, and they're split up into groups, and they're named right here in the upper left-hand corner of what this type of a group is. So we've got alkane, alcohol, ether, and amine. And yeah. And so don't worry so much about what that means right now, but the worksheet here, the activity is going to ask you to try to make some connections there based on what you know about what those structures look like. Some other information that we get here for each group is the molar mass, which is the size of the molecule. So how much does a molecule weigh? Larger molar mass, larger molecule. We get something called the dipole moment in a unit called debias, which is actually a measurement of the polarity. It says it down here somewhere. Yeah, here. The dipole moment is a measure of the polarity of the molecule. So how lopsided are the electrons in that molecule? Are they pulled more to one side or the other? If they're pulled more to one side, you're going to get a higher value here. So the fact that this is 0 tells us that these molecules are completely nonpolar. They don't have any preferential pull from one side to one side or the other. And so that we can compare to some of these other ones where there's something different going on. All right, the next one is boiling point. So this would be the temperature at which this compound boils. Let's think again about what boiling is. We talked about that with physical and chemical changes. Boiling is not a chemical change. Boiling does not break apart the molecules. All it does is separate the molecules from each other. So we're not talking about the forces inside molecules. We're not talking about breaking out bonds. We're talking about molecules attracting each other or being pulled apart from each other, but the molecule still stays intact. When you boil water, you don't make hydrogen and oxygen. You still have water. It's just water vapor, right? Physical change, not a chemical change. And then the final column is water solubility in grams per 100 milliliters H2O. So this is how much of this stuff can dissolve in 100 milliliters of water. If the number is very low like this, we would say this is pretty much nonpolar. If the number is very high, we would say it is, or not nonpolar, insoluble. It's not soluble. If the number is very high, we would say that it is very soluble. And some of these, if they're liquids themselves, can be infinitely soluble, because you can put as much as you want, and even though you now have more of this substance than you do water, it's still going to keep mixing. So there's no limit to how much you can mix with water. And so you can see there's some changing in that solubility as well. All right, so that's sort of the basics here. So now you can start getting into the questions. And remember that in these types of activities, the questions start quite easy, and that's by design so that you can just answer them. Considering the dipole moments of the molecules in table 1, which functional group is most nonpolar? So you go back up here, and we know that this column is measuring polarity. So we go through and say, well, okay, well, the ones that are all 0 are the least polar, right? They're the most nonpolar. Some of these other ones, they're not measured, so we don't really know, but we definitely know the zeros are all nonpolar. So we can say that pretty confidently. Whoops. Too far here. All right. So in general, do polar compounds have higher or lower boiling points? So you can go back up here. What would we consider polar compounds? Well, that would be like this one, this one, this one. These seem more polar. So in general, are those more higher or lower boiling than this? Well, what do we mean by in general? Well, one way that we can think about that is comparing similar sized molecules. If two molecules are the same size, one is polar and one isn't, that's really the only difference between them. So that might be a good explanation for any differences we see. So if we look at a one here that's 44 and here that's 46 and here that's 46, what are we seeing about the boiling points versus the dipole moments, the polarity? Same thing as we look at some bigger ones. If we look at an 86 versus an 88, are we seeing a difference there? And so I don't want to tell you answers here because this is meant to be kind of subjective. How do you see this? But then ultimately, when you get to some later questions, 3, 4, you should be able to make some larger generalizations about what in general is happening as these things change. Okay. So then it kind of keeps going through that, looking at some different things. Make sure you're reading some of these informational sections that give you a little more information about what these parts of these molecules do to affect the physical properties. The overall goal of this activity is to connect structures, the shapes, and what kinds of elements are connected together to physical properties like boiling point, like water solubility. So things that we can observe in the lab connected to what those structures actually look like. And what you want to be able to do by the end is a problem like number 5 here, which says, without looking up any information in any tables, identify the molecule in each group that would have the highest boiling point and explain why. So without looking up any data or numbers, by the time you work through this activity, if you've understood it, you should be able to look at a structure, 3 structures of a molecule. And by the way, this is sometimes confusing. The group is horizontal. So these are the 3 molecules of group A. These are the 3 molecules from group B. Group C. Group D includes this line structure of this cyclopentane, and then group E here. So within those 3 molecules, which one's has the highest boiling point? And if you understand how structure influences function, so how the structure influences the boiling point, then you should be able to understand that. If not, go back to some of those previous questions, make sure you understand them. Ask me, ask your classmates. We can talk about it in lab on Wednesday. We've got those kind of 2 days off in between the modules on Monday and Tuesday. So you're welcome to schedule some time with me to talk about them there. I'll be around this weekend also if you want to schedule some time then. Let me know if you're having some issues. And because this comes from some other source, make sure that you can skip things that say like number 7. Actually, I don't think you can see that here, but number 7 said read the problems or read the book and do your assigned problems. We don't have that here for this part, so you can ignore that. All right. Not seeing any questions in the chat here. Let me check on Discord. I'm not seeing anything there. Okay. Again, let me know if you're watching. If you have questions, I will try to answer them as soon as I can. Okay, let's take a look at the data from lab again. So yesterday in class, we got a chance to take a brief look at it, and we noticed some issues where the calibration curve here seemed like something was going wrong because we were getting a lot of negative values, and that can happen if there just isn't that stuff in the sample. But in order to make sure, let's construct a calibration curve ourselves and just give it a quick check and see what we're getting. So here's our standards that were run. There was a standard at 5, at 2.5, and at 1.7. And you know what? That is not the actual concentration. That is the dilution amount. So I'm going to have to hold off on this because I got to get back to lab and actually figure out what these numbers mean. So we're going to have to wait on this until next Wednesday because I won't be back on campus until Tuesday. So I didn't realize this before I left yesterday, but I will have to check the actual concentrations before we can construct that calibration curve. So we will do that together in lab on Wednesday, and I'll make sure to have everything ready for you at that time. So sorry we couldn't do it now. Just hold off on that. Keep sending me your questions. Hopefully the rest of the module works out okay for you. I'm excited to see how you were able to learn this stuff. Next module is number 4, which is the midterm. So by the end of that, you should be caught up and really have a good handle on the material from the beginning of the class until then. And directly after that, which would be spring break, just after spring break, we will meet to start. Or no, that's not quite spring break yet. It'll be just before spring break. 1, 2, 3. Yeah, just before spring break, we will meet individually again and talk about how you've met the objectives for the first half of the class, and you will give yourself a midterm grade. All right, so let me know again if you have questions. Keep them coming on Discord or email, and I'll get back to you as soon as I can. You can always schedule appointments with me online or on campus, and I'm on campus generally in my office between like 3 and 4 on Tuesdays and 2 and 4 on Wednesdays, but I can also be there other times if you want to meet me. So let me know, and I will see. Otherwise, I will see you on Wednesday. Bye, everybody.